All right, hi. Today I'm going to talk to you about green software engineering, and the subtitle is The Curse of Methodology. It's kind of hard. I'm Abram Hindle. I'm from the University of Alberta in Canada. That's in Edmonton. And my email is hindle1@alberta.ca. So, what I really like about software energy is that it lets us relate the work that software does, the work that computers do, to actual physical measurements of effort or work. When you turn on a light bulb, you expect it to produce light, right? And these light bulbs are rated at a certain power rating. And this kind of power rating, you'll just have to excuse me, there is a firmware issue with this laptop, and it causes some problems. Okay, anyways. So the light bulb, it takes, like about 40 watts of power to operate. It turns out that, this laptop right now is probably at 13 watts, right, producing this, this presentation, which is pretty good. The neat thing about it is that now we can relate the work that software has to do and computers have to do to the actual cost or the effort. So I think that's a really neat thing, which means that we can actually measure the cost of computation. Unfortunately, at least in North America, the majority of electricity is generated through coal-fired power plants, which means that any electrical use basically has a carbon footprint. Any electrical use has an impact on things like climate change and the environment. But it also means that we know the price of computation. The price of computation is basically the electricity that it takes to execute your task. And that's pretty nice because that means that I know when I do deep learning on my computer at home, after about 4 hours, I owe the electrical company 12 cents because I've used a kilowatt hour. The neat thing, though, is that this means that you actually have true costs of computation even after equipment purchases have been done. In data centers, electrical use and cooling oftentimes make up a huge amount of the actual equipment cost. Okay. When we measure software energy consumption, we have to decide on how we're going to measure it and what the purpose is. Are we measuring a task or a service? A service provides continuous work. For instance, serving up web pages continuously to end users would be an example of continuous work. Playing a game, giving you entertainment hours would be an example of continuous work, right? Because you choose for a certain amount of time to play that game. So maybe your Pac-Man is 10 watts, but you're playing Halo is costing you 200 watts. This is analogous to how you use light bulbs and light. When you turn it on, it's 40 watts. When you turn it off, it's not using anything, but it's providing a service while in use. This is different than a task. We normally don't ask things to continuously compress files. We normally don't ask things to continuously move files around. These are tasks that have a start and an end. They have a power rating while they're running, but the integration of that power over time will be the energy consumed. The energy consumed is joules. So basically 1 watt second, so 1 watt over 1 second is about 1 joule. 1 watt hour is about 3,600 joules, and you'll just have to excuse the changing. It's really quite annoying. Just give me a sec. So 1 kilowatt hour, which normally costs me about 12 cents in Edmonton, is about anyways. Okay. One use of software energy consumption is to rank apps or to rank software by their energy efficiency. And I don't just mean mobile apps. You can actually rate, say, Java collections. You can relate different libraries for their energy efficiency. This is quite useful because now you can say how efficient something is at doing something. But it doesn't mean that just because something is more energy efficient it's something you should use it. There might be a reason why something is more inefficient or less inefficient than something else, and it could have something to do with usability or other kinds of features you rely upon. So Zhang et al., Hindle et al., Jeber and et al. Have all tried to address app ratings, but in terms of energy, but there's also the issue of which libraries to use and things like that. Now, in order to get there, we actually need to measure energy consumption. And this turns out to be quite a difficult task for developers. Okay, so there's multiple kinds of measurement that we can do, and this is very disappointing. I apologize.
Do you want to use another laptop?
No, that's just going to be a pain to transfer. Don't worry about it. All right.
Can you cancel the presenter mode maybe and just show the slides?
I don't think that's going to make a difference.
No?
It might, but I kind of doubt it. No. Okay, we're not going to deal with technicalities after this point. Okay, in terms of measurement, oh my god, this is really bad. All right. Oh my god. Okay, I apologize for the technical difficulties. Normally it's not this awful. Regardless, all right. So software measurement is really quite hard. Because what you want to do is you want to decide what you really want to measure. And there's a problem. If you measure just like, if you measure just the CPU or the memory systems, you're ignoring I/O operations and things like that. And you're also not necessarily looking at the other peripherals. So you have to make a decision whether or not you do component level measurement or whole system measurement. There's also the issue of how often you sample. How often you sample determines what level of granularity you can look at inside your running system and how you can relate traces. So work like Lee et al., they had megahertz level sampling, which allowed them to attribute instantaneous energy use to source lines. This is pretty good, but it also ignores the fact that you can ask for work to be done that will be delayed. Gupta et al. Also looked at things of how to look at the traces of library use and figure out how the libraries were actually being, what their energy traces kind of look like. Once we measure, we can start doing useful things, because measurement is actually pretty hard. Usually you need a physical measurement device, or you need some kind of thing that reports back to the computer the energy use. And this is very difficult for developers to deploy and use. So what most researchers try to do is they try to take those measurements and they try to produce models from those measurements. And those models, they oftentimes are stuck in one context, whether it's Windows Phone, whether it's Linux, whether it's ARM processors or x86 processors, whether or not it's an OLED screen or a different kind of screen. They're kind of stuck in these contexts of what hardware is available, what peripherals are available, and even what the task of the model is supposed to do. Do we want to estimate whole application energy use, or do we want to estimate power use? Or do we want to know what the real cost of this one method is, or this block of code? Or, alternatively, what the cost of a refactoring is. Like, Sayan et al. Did a lot of work on refactorings. So, you basically have to decide the granularity of measurement, and then you produce a model which deals with that. And this causes a big diaspora of many, many models out there, and it means that if we're trying to deal with other people's work and other people's papers and do replications, that we have to share that context at the same time, which means it's kind of difficult. But nonetheless, there are lots of models suggested. Some work better than others, some work in certain contexts, and things like that. So, what challenges does software energy consumption actually face? Measurement has been done, models have been created, but there's still not enough. We still don't have good answers to like, should I refactor for this reason? What's the cost of this using this library? There's a lot of energy questions out there that still can't be answered definitively. They might be answered in certain contexts, like say on Android. So what are the challenges that we face? Well, one of the challenges, the main challenge comes from community. With the lack of a coherent community, we really have a lack of coherent and shared data. We have a lack of shared tools. We have a lack of shared benchmark. And we have disagreement on even measurement methodology. So this kind of challenge is a big deal, which means it's an open research area. Please come and join. These are big challenges, and they're not necessarily doable by just one person, but there's lots of parts that can be bitten off, and one person can address them. One of the largest challenges in this area is really the lack of data. There's no shared FLOSS or open source energy data, and there's not a lot of performance data either. There's a little bit more available performance data, like you can get hard clock stack traces and things like that. But for the most part, you don't have a lot of access to a lot of data, and most people aren't measuring energy because it's actually kind of difficult. So you don't have this data. Furthermore, researchers tend not to share a lot of the data. There's actually more available data in household measurement of energy than there is in software and computer measurement of energy. Furthermore, there's a good reason why this data is missing, and I'm not pointing fingers at anyone. It's because it costs money, time, and resources. The data that I generate in my studies is kind of heterogeneous compared to other data that people generate in other studies. Their data is kind of heterogeneous to me. It depends on your experimental treatment. One run of one app under one test load is not equivalent to a run of another app under another test load. Furthermore, the tests under load, they produce different results. There's some kind of non-determinism, so we actually need to run these tests numerous times. Furthermore, CPU is not enough when we model and when we address software energy. I/O is computation now. In fact, in the Haskell language, they treat I/O as a specific computational operation. They use monads to represent it. It's because it is computation. So if we have models that only do memory, only do CPU, only use RAPL from Intel, and only work on i5 processors, we miss out on the energy use of wireless transfer. We miss out on the energy use of disk transfers, network transfers, and using our big honking GPUs. They use a lot of energy. There's also the question of, if I'm measuring a software system, do I measure just the client or should I measure the whole system? Like if I'm running Hadoop, do I measure the whole cluster or one node? Do I measure the cluster under load with other clients? It's not necessarily clear. Another issue that you face when you do software energy consumption research is the non-determinism of software and hardware. Your software will act differently, especially in the mobile case, based on location. Your software will act differently based upon the past tasks that you just did, leaving it in a different CPU state. The file system fragmentation of running tests over and over again, and the memory fragmentation will have an effect. Also, you don't control the electromagnetic spectrum. If someone turned on the microwave, you had no choice but to deal with it. How can you control for people turning on the microwave during your test? Maybe just unplug it. There's also network congestion. This all boils down back to the big challenge, which is community, in the sense that it's very fragmented and diverse. There's basically like 4 main diverse interests: smart city energy, hardware energy, software energy, sustainability. And all these different communities ranging from green software engineering to general software engineering to requirements engineering to more practitioner-based or more mobile-based kinds of groups, they all have different interests. And so the publications in this area are spread across a lot of regions, and it's hard to maintain visibility. So you got fragmentation, you got spread out diversity in that sense, but you also get a lack of reviewers who are aware of energy issues. So, what can you do right now? Well, there are a lot of pitfalls with software energy research, but every single one of these pitfalls is basically an open question for a paper, or a couple of papers, or a thesis. So, let's think about this. If I make a test and I test an application for software energy use, what's the coverage of my test? Does test coverage really have an effect on it? Do I need to cover all of my source code lines in order to get an accurate test or not? In order to get an accurate read of software energy? That's a good question. Also, if I test multiple versions of the software, do I have to test each version of the software equally? My measurement, if I rely on the battery to provide energy information, how reliable is that? And then we're also left with the issue of test realism versus test isolation. If I'm testing in the cloud, should I test on an empty cloud such that I can isolate how my tests actually run? Or should I run it under realistic assumptions that it's a multi-host cloud? Other pitfalls include platform differences. Right now, no one can answer the question, what's the real difference in energy use between Linux and Android? They're not quite the same thing. They're a little different. They share mostly the same kernel code, but we don't have a good answer to that. How should I control in a model for switching from Linux to Android? How should I control in a model for switching from Android to Windows Phone? How should I control in a model switching from Linux to Windows? This stuff isn't dealt with. Another thing that we don't tend to deal with is things like how temperature affects software energy use. Temperature affects physical energy transmission because it increases resistance. But temperature also affects the cooling systems on your computers. The hotter they get, the more they have to cool. Furthermore, there's other issues like Is there a real difference in CPU use between me pressing my fat finger on a phone to click a button versus getting like Monkey Runner to click that button? Maybe Monkey Runner is a lot lighter because there's a lot less interrupts. These are kinds of questions that really haven't been addressed yet in the community, and these are things that could be immediately researched. They're not necessarily the future, but they can be done right now. So, what's going to happen in the future of software energy consumption? Well, we'll probably have better methodology, right? We'll probably agree that tests need to be run multiple times due to the non-deterministic aspects I brought up. Furthermore, more of the analysis will probably be evolutionary aware. If I compare Firefox versus Chromium, it's not really fair to compare one version versus the other. I should actually be comparing a range of versions because software energy profiles change over time. And the latest, greatest is not going to be the current software energy use in the future, and it wasn't in the past. So we kind of have to compare windows of versions. Furthermore, why wouldn't you want to study multi-version analysis? At least in this conference, we're oftentimes related to other maintenance work and other maintenance conferences. So you're already dealing in a multi-version world where you're producing the next version. So understanding the deltas between things is important. I really don't want developers to have to measure software energy anymore. They don't necessarily have a lot of the training to do really good measurement, and they often don't have the equipment. So what I want, and I think what the future is going to hold, is we're going to start taking a lot of these lovely models that we have produced, and we're actually going to start bringing them into the IDE. Visual Studio already has an estimate on energy use based on CPU, but it doesn't necessarily have it on I/O. So what we're going to get is we're going to get developers delegating measurement and recommendations to smart agents. And like in May's talk, we're going to have cloud testing services. So May showed that big row of machines. Imagine having all those energy instrumented as well. So you don't need to buy them, you just need to buy a subscription, submit your test off, and boom, it gets tested off against a lot of different devices, and you get to understand what the impact of your change actually was. One of the biggest things that needs to be dealt with is the fact that server-side software is changing a lot. It used to be we had issues trying to estimate cloud use, but now containers like Docker have come along where it's basically multiple mini VMs in one virtual machine, and it's kind of hard to estimate the energy use of that load. So what's going to happen is we're going to have to further address cloud and containers and see if we can basically suggest, this container running Mongo and PHP and Nginx, it all together, that container is going to cost you a certain amount under certain loads. And you're going to have to understand that the load balance, or the load that that system is under, is going to be different over time. But right now, we don't have a good way of estimating whether or not containers even have much of an effect on energy use at all. Furthermore, from the requirements angle, sustainability will become a requirement. Much like May brought up that you have to choose basically between your features and the cost to the user, the features that you do choose will have an effect on your energy use. So you'll have to look at your context, and you'll have to weigh whether or not certain features should be deployed given their energy envelope. And it all comes down to the fundamental of software engineering, which is that we're solving problems economically. The almighty dollar reigns supreme. So in order to address this, we have to address the actual costs of the functionality. So sustainability will become an important line ticket item in requirements, and that power envelope will have to be addressed. Finally, I said it was hard, I said it was difficult. A lot of it has to do with training, and there's a complete lack of training right now. Our electrical engineers get the training, but our software engineers do not get the training. There's also a lack of resources to educate people on software energy consumption. There's no MOOCs, there's no syllabi, there's no suggested curriculum. There's some information on sustainability, and sustainability is probably a good way to motivate this. But fundamentally, we lack education on this topic. Candy Pang, my PhD student, she went out, she hassled a bunch of developers and asked them what they knew about software energy. Unfortunately, it wasn't a lot. So there's a lot of room for education, and we also have to educate existing developers. So, in conclusion, I think what we really got to address is, first and foremost, the community. The community needs to come together and maybe make some shared repositories or have more coherent discussion about software energy use. Software energy use is really neat, because we get to actually compare software effort, software runtimes versus physical measurements of work and effort. We face many challenges ranging from community, shared data. We face many pitfalls, such as how much test coverage do we need to have a representative test? What tests are representative? The future will be sustainability, the balance of features versus energy use, as well as education, combined with no longer requiring developers to really know how to measure energy, because they'll rely on, say, an IDE helper like Pluggy the Plug, which looks sort of like Clippy, as well as they'll also be able to suggest what their cloud loads will look like. Furthermore, we'll also require, a lot of the future research will be on basically how do we address the evolution of software over time with respect to energy. So, final conclusion, we kind of need to come together as a community. And we need to help build shared data sets, and we need to help build shared tools such that we can actually measure against each other, as well as shared benchmarks, which don't really exist, and agreements on methodology. So I invite you to join the field of software energy consumption. There's a lot of open questions. There's a big future to it. It's getting popular, and data center power limits are of an ever-increasing high-cost concern, as well as mobile users. They also want to keep using their phone, and they don't want it dead because your app had an ad network and killed everything. All right, thank you.
Okay, I will actually start. My first question is about community. You talked about community, but then you ended up listing most of our conferences. I believe people should also look at what researchers in measurements are doing and the researchers in Node are doing, because research in this area is really multidisciplinary. What do you believe? What do you think?
Yeah, so there are a lot of conferences that have an electrical engineering flavor to them, a lot of embedded ones, like there's a whole context of embedded sensors. So the EEs have a lot of good ideas. But what's important to realize is that oftentimes they have good models of their sensors because they're actually pretty small. And they have data sheets. And they're not really big, complicated systems. The phone that I have right here in my pocket, this is like running an operating system designed in 1970, upgraded, whatever, and it's, Unix. And it's way stronger, way faster than the computer I bought in 2000, right? And so when it comes down to electrical engineer, a lot of time their work is already done, and it's kind of up to a software engineer at this point. So there is a balance between the two, but there's a weird separation between the communities and strange interactions. So you're right about measurement from the EE perspective, but there's also the need for blame of use in software, and the E's aren't so great at that. So there's kind of this weird interaction between the engineering groups.
Thanks, Abram, for this inspiring talk. So far, developers are striving to improve the maintainability of the code, the understandability. And now your message is that they should also be aware of the energy consumption, how to improve that. Don't you think, though, that these are two conflicting goals? Sometimes, the energy efficient code is not the most probably easier to maintain code or the most readable code.
I agree, but in a lot of cases, we're not developing high-performance, heavy computation software. We're not pushing matrices really hard. A lot of our software sits idle for the most part. So what can be done is that developers can be pushed towards more APIs that are more energy efficient for them to use. APIs that allow their applications to go to sleep, such that energy can be saved. So there's context where, yeah, you're right. If I forego abstraction for the sake of performance, I hurt maintenance. But there's a lot of cases where I can improve stuff just via nice APIs that take advantage of what the operating system, what the hardware has to offer. So it goes both ways.
Okay, May, and then okay, go ahead. Go ahead.
Oh, there's only one. Oh, sorry.
No, there's another one.
Okay, go ahead.
Oh, yeah. Okay, so we squatted the microphones. Good. Okay, awesome. You got me at platform migration and the impact on sustainability and on energy consumption. Has anyone investigated the impact of migrating software from mainframe to normal computers?
In terms of energy use?
Yes.
I'm not totally aware, but I know that most patterns of migration are to run it on a VM on another machine. So IBM will oftentimes move like a whole mainframe to a VM on another machine. I would assume that there's an energy efficiency gain even running a VM there, just because the hardware has improved so much over time. Like our modern hardware is very efficient for what it does.
Okay.
So I'm not aware of work. I probably missed out some, but I think it's more efficient now by moving mainframes to VMs, just because the machines are just far better.
Okay, so I work at a company that does it differently without a virtual machine. So let's try it. Let's do it.
Okay, cool.
Let's
We'll talk after.
Okay.
So getting back to the previous question, you could just view energy consumption as another non-functional requirement, which it kind of is, and we're always doing trade-offs of non-functional requirements. We understand that they often conflict with each other, and it becomes part of the bigger equation. The question is, my question is, often when we do measurement, instead of measuring the thing we want to measure, we have to use a proxy because those are the things we can measure. The traditional approach to measuring computation cost, at least in terms of people with old-fashioned CS degrees, is computational complexity. Have you thought about how you might correlate energy consumption against computational complexity? Is there anything to explore there?
Yeah, there's, so Laurie Pollock's group, they have some work at ICSI, which was called SEEDS, where they basically search-based switched collections on people, Java collections. And they basically chose the collection class that was the most efficient for that product. And it was product specific, because if you have different use cases and different profiles, it'll be a little bit different.
So I guess what I'm thinking of is if you had a really big program and you could do a computational complexity analysis of its various parts, and then found out how it ran and what the energy consumption was like, you would have two different views, the classical view and the instrumented view, and be able to make predictions about how often you care about the complexity argument and when sometimes it's not the right thing to consider. This would give us, just using static analysis, better intuition about what might be a problem, what might not be. So
I was thinking about the idea of green big O, and what green big O does is it takes into account, it basically weights your memory use, your I/O, and your CPU. So you have to do multiple big O's, and you have to put modifiers on them to say which one's important for energy use. Memory use might not be super important if you've already been allocated that memory and it's done, right? It's got to be charged up. So a green big O would have to be a multi-view combination whereby you've chosen, I care about I/O a lot, especially network messages, and the CPU isn't as important as network I/O. Something like that.
That's a great metaphor.
Right. Great talk. I do agree with you that money in the end is what kind of helps us make the decision. But even in the past, we've used economic motivators, but not actually attached a dollar value at the end of it. What makes you confident that you'll be able to do it when it comes to energy? How can we finally attach a dollar value to these things?
Oh yeah, like if you have a server that's got 2 GPUs in it and it uses 1 kilowatt hour, at least if you run it in my house, it'll cost me 12 cents. And I know how much that costs. That's what the distribution cost is. So I have that, and we can add that into the lifetime. So we can say, well, we're going to run this nonstop at Abram's house, so he's going to be spending 12 cents an hour running, I don't know, deep learning on ads. We'll do that. And then we multiply by the lifetime of the machine, 5 years, and we've got an energy cost that we have to pay. And it's kind of neat because we could pay less. We could do something more efficient, or do it less, or do an alternative, and it could require less effort to do, and we could get it there for less. There's also other ways to do it more inefficiently. So there's these neat trade-offs we get to make, but I think the true pricing is one of the neat aspects of it, as well as it has a sustainability aspect to it, because the more it basically means if you compute in an environment where your energy is generated that has a carbon footprint, you do have a carbon footprint, so it's a bit of a concern. I don't know if I answered your question.
Yeah.
Okay.
Okay. Oh.
So if I'm writing an app that will run in a public cloud, why should I care about energy efficiency if I'm getting billed by the hour and not by the joule?
Because they're basically already billing you for that. They're billing you for having the CPU allocated for that time, and they're billing you for having that CPU already allocated for that time, and there's a good chance that they will bill you for the energy use. So if you use, in the future, I suspect what you're going to find is that it won't be just CPU hour, it'll be actual CPU hour, like how much of that hour you are actually awake. So you'll get a good discount if you are in a more idle process than a heavy process. So CPU hours in the cloud are kind of weird because oftentimes you have virtual CPUs. And if I've got a box and it's mostly idle processes, I can load it up with like 40 virtual CPUs. But if they were all doing matrix, or they're all doing linear algebra, I would be limited to the number of cores I have. That's like the number of safe virtual CPUs. So the power will be basically this envelope that we'll probably even see later. I bet you AWS will charge it for us in the future, just as a way of saying, hey, you guys stay in within this certain amount for these devices. Because oftentimes on the racks, each unit is allocated a certain power envelope of the max power it can use. So they'll have to do something about it if you're going off the rails.
I think that's the first step to actually getting the almighty dollar to intervene.
Yeah, and cooling costs, those are immediately noticeable.
Last question from...
So it seems like your research has quite a few potential customers, right? You could have, the cloud providers, you have developers as well. Is there a particular customer group that's more receptive to your research? Who's more hesitant? Do you have any impression?
I've had some interactions with mobile app developers, and they've been somewhat receptive. Like we solved one of their bugs. They didn't realize they had like it was an MVC kind of framework, and they had an extra listener that was always getting hit with an event, and it was using CPU unnecessarily, basically moving the power up to the max. And we found it, and we told them about it. Well, we found the power issue. We told them about it. They found out what it was. They thanked us for it. So at least from the mobile side, there is some benefit because you don't want to get a bad app review for using everyone's battery. But I think for dollar value, it's probably more the data center, probably more people who actually have to pay for the equipment itself and do the cooling. They probably care more about the software energy use, because the hardware does nothing without us commanding it to do something, which is why software energy use is important. It is our commands to hardware to execute, and it costs energy to do so.
Okay, let's go. Oh, two. What?
Hello, Abram. Thank you very much for your talk. Because now we know that we have some knowledge related to energy, I would like to know if it is possible to include this information in the compiler to try to make or to compile or to make more efficient applications considering the energy in the process of the compilation.
Yeah, but in general, if your compiler does any kind of optimization for runtime, usually it's already doing the green optimization. I think where compilers have a problem is when we want programs to use APIs that are more energy efficient, and is that really the compiler's responsibility at that point? I'm not totally sure. So I think there's a lot of room for stuff in the compiler and stuff outside the compiler to help push developers into a more energy efficient direction. But we have to recognize that after we've dealt with runtime and CPU efficiency, the other stuff gets a little bit harder, especially like disk use and network use. So the compiler might not be so great at that, and that calls for more dynamic analysis, which means it might not be the purview of the compiler.
Okay, thanks.
Very quick and last question.
A very quick one then. So the title of your talk was Green Software Engineering, and you've mostly covered energy efficiency of applications. So I'm wondering, what can we do to make software engineering itself green as well?
Oh, well, there's whole sustainability. So Patricia Lago et al., they focus a lot on sustainability, and sustainability has a lot of interesting questions. And sustainability can be applied to the software development process itself. I'm not sure work that specifically asks for software processes to be sustainable, but it is an open question, and I think you just stumbled upon like a possible paper. So.
Thanks again.
All right, thank you.